Hello, welcome to my talk all about fluids. This talk is on the basic equations for the turbulence modeling. Part 1, Reynolds averaged Navier-Stokes equation. In this talk, I will introduce the method for averaging in the fluid dynamics, namely time averaging for the continuous functions or the ensemble averaging for the sampled system. And then I will show how the Reynolds averaged Navier-Stokes equation is derived. This is the fundamental equation for turbulence flows, and it is the basis for establishing the turbulent transport equations for Reynolds stress component, turbulent kinetic energy, and the dissipation rate. For fluid dynamics, we might have two different flows, steady flow and unsteady flows. Here, we're talking about the turbulent flows. Principally, turbulent flows are inherently unsteady. For some flows, the mean flow is steady, with small turbulence superposed on the main mean flow. See the figure here. The red line is the mean flow velocity, and the fluctuation of the velocity is the turbulent velocity. So the average velocity of a steady flow is given as this. Here, t is the entire time period of the problem. As such, the averaged variables would be time independent. It should be noted here t is a time period long enough for the steady averaged variable, not necessarily to be infinite as shown in some textbooks. As such, the averaged variables would be time independent. For the unsteady flows, as seen in this figure, we could have an always time-dependent average variable superposed on the small fluctuating variable. So the averaging is made as given in this formula. So here t is the sectional time period, a time period longer than most of the turbulence time scales, if it is not all, but it would be significantly shorter than the entire time period of the problem. Therefore, the part time averaged velocity is still time dependent. For the unsteady flows, it can be the unsteady flow driven by the unsteady boundary conditions, or simply the spontaneous unsteady flows, such as the vortex shading of the cylinder in this video. The unsteadiness of the flow of the cylinder is caused by the vortex shading, although the incoming flow and the boundary conditions are steady. The spatial averaging is the volume averaging of the physical parameter at the geometric center of small volume, given by this. See here, the center point xn is at the geometric center. Or we might have the fluid momentum center of the small fluid element defined as this. Here, the average velocity is calculated at the momentum center of the fluid element, theta v. Nowadays, in deriving the Reynolds averaged Navier-Stokes equation, we don't use the spatial averaging as shown in here. However, in CFD, such as the method of finite volume, we may use the spatial averaging, and we normally take the physical parameters at a certain point within the fluid element for representing the physical parameters. Ensemble averaging was given by Reynolds in his derivation in 1895. His averaging scheme is given as this. According to his own word, U bar here is the velocity of x direction at each instantaneous center of gravity of the fluid of a small volume delta V. However, this expression is not for today's understanding for the problem, since sigma rho has no physical meaning here. And then Reynolds also gave the component momentum at the center of gravity, written as this. And we can easily derive the velocity expression, the mean velocity plus the fluctuation velocity. Nowadays, the ensemble averaging for the timed samples is given as this. Here, we assume we have m samples within the short period t here. So this averaging of the velocity is a constant for the time period t. And again, the velocity can be expressed as this. So here, we suppose in a sampled system, we have m sampled points within the time period. Thus, the average velocity is still time dependent, as we have seen in many textbooks and papers, such as the U-length, unsteady length, T-length, transient length. Following the Wilcox's book, in the talk, I will use capital U and capital P for the mean velocity and pressure, and the U prime, P prime would be the fluctuating velocity and pressure. So all the averaging methods mentioned in the previous slides are linear operator. In a simple averaging, we have an expression as this. It should be noted that the averaging value U would be a constant for the averaging operation, but it would be both time and spatial dependent. Therefore, the averaging of the averaged velocity here is given as this. So, the averaging of the averaged velocity would be the averaged velocity itself. The averaging of the fluctuating variable would be 0. Take the velocity u as an example, and take average of this expression. We have this, and it can be written as this. So we have the expression as this. From this, we can deduce the average fluctuating velocity would be 0. Here, we must mention the averaging operation and the conventional mathematical operation, plus, minus, and the differentiations, integrations, and the summations are all linear operations. Thus, the order of the operation can be swapped because of the linear operators. In here, we look at the averaging of the fluctuating velocity derivation with regard to time. This is the expression, and the averaging of this expression, we have expression as this. So since this part, we can swap the order of the differentiation and the average. So this is the expression for the averaging of the velocity derivation with regard to time. Therefore, we have the expression for this. That means the derivation of the fluctuation velocity with regard to time, its average is 0. And this actually can be easily obtained because we can change the order of the averaging with the derivation, and this can be easily derived. For the incompressible flows, the conventional expression of the continuity equation is given as this. In details, the differentiation form of the continuity equation is written as this. Here, u, v, and w are the velocity components. And this is equivalent to the expression as this using the indices. So in Einstein summation convention, this continuity equation can be written as this simple form. So if we take the average of the left-hand side, we have this, and we can exchange of the operation, the averaging operation and the derivation. We have this and this. So we have the continuity equation for the mean flow velocity as this. Now we use the average and the fluctuating velocities. Ui equals capital Ui plus u prime I. So the continuity equation would be in this form, considering the continuity equation for the mean velocity. So we can have the continuity equation for the fluctuating velocities as this. Therefore, we can see for the incompressible flows, the continuity equation for the instantaneous, the averaged, and the fluctuating velocities have the same form, see in the circles. The Navier-Stokes equation for incompressible flows can be written as this in Einstein's summation convention. Here, Ui, Uj are the velocity component. Ij equal to 1, 2, and 3. Fi is the body force per volume. P is the fluid pressure. Nu is the kinematic velocity of the Newtonian fluid. Ui, Uj is the tensor of the double velocity vector. Use the averaged and the fluctuating velocities and the pressure. We have the Navier-Stokes equation as this. Take the average of both sides of the equation. We have the expression as this. This term can be written in this. And we can swap the order of the average and the plus. So we have the equation as this. Now in this slide, we will examine each term in the average the Navier-Stokes equation as this. Term 1 to 5. So term 1, we have this, And we can separate this into this. Because of the average of the fluctuation velocity is 0. We have the expression as this and this. For the second term, we can separate each term into this expression. Now, considering the mean velocities, capital Ui and capital Uj, would be constant for the averaging operation. Thus, we can take the mean velocity capital Ui, capital Uj out of the average operation here and here as well. Now we can see the average of the single fluctuating velocity u prime j and u prime I are both 0. So we have the final expression for the second term as this. So from this mathematical manipulation, we can see the averaging of a single fluctuating velocity is 0, but the averaging of the double fluctuating velocities is not 0. And in turbulent flows, this term would be very important. The third term is for body force. In most cases, the body force is given, so it is not relevant to the fluid turbulence. Thus, its average is itself, so the expression is this. For the fourth term, the pressure gradient, we can separate the expression as this. And obviously, for the pressure fluctuation, its average is 0. Thus, we have the expression for the fourth term. Similarly, in the fifth term, we have the expression as this, and we can separate the expression into two terms. Now we can see this term would be 0 because it is for the averaging of the fluctuation u prime I. Therefore, the fifth term is given by this. Now put all these terms together. We have the Reynolds averaged Navier-Stokes equation as this. This equation is for the averaged velocities and pressure. And a significant difference for the equation is that this Reynolds averaged Navier-Stokes equation has an additional term when we compare it to the original Navier-Stokes equation here. And this term is all about the fluid turbulence and causes the tremendous difficulties for solving the fluid dynamic equation. Turbulence modeling is a way to try to find the solution for this term. This equation can be written in this form. So this is the conventional Reynolds averaged Navier-Stokes equation with the Reynolds suggest tensor defined as tau ij equals minus average of the double velocity u prime I and u prime j. This equation can be derived from the conventional symmetric strain rate Sij and the mathematical operation on this viscous stress tensor. We have this expression and this. And for incompressible flow, this term would be 0. Thus, this term would be same as this term. Use the newly proposed asymmetric viscous stress tensor in the reference below. The Reynolds averaged Navier-Stokes equation can be given in this form. Here, Aij is the asymmetric strain rate tensor defined as this. Now we have the conventional Navier-Stokes equation in a form as this. Here, the mean and the fluctuating velocities and pressures are used. And from the previous slides, we have also the Reynolds averaged Navier-Stokes equation given in this form. So if we subtract the Navier-Stokes equation with the Reynolds averaged Navier-Stokes equation, we can obtain the Navier-Stokes equation for the fluctuating velocities and the pressures as this. If we use the continuity equation for the incompressible flow, this, and we can write this Navier-Stokes equation for the fluctuating velocity and the pressure into this expression. Now we can see for the turbulence flow, the mean variables and the fluctuating variables are actually linked together. Mathematically, for the mean flow, the Reynolds stress tensor, this term from the flow turbulence, would be an important influencing factor which would change the flow pattern of the mean flow. And in the Navier-Stokes equation for the fluctuating velocities and the pressure, we can see the mean flow velocities uj and ui are engaged, which can be regarded as the generator of the flow turbulence. Or from the point of view of energy, it can be understood that the engagement of the mean velocities here is a way transforming energy from the mean flow into the turbulent flow.